On the morning of October 7th, 2025, a new signal rippled through the world of astronomy. It was not a transmission, not a sound, but a release. A set of images quietly uploaded to the European Space Agency's data servers. Within hours, they ignited the imagination of every scientist, journalist, and skywatcher who laid eyes upon them. These were no ordinary photographs. They were ghostly, almost reluctant glimpses of something drifting between the stars. The interstellar comet known as 3I Atlas. What made the release extraordinary was not only the object itself, but the way it was seen. The images came from a camera orbiting Mars, a machine designed to study the red planet's thin skies and dusty canyons, never the void beyond. And yet, against all expectations, it had captured something that by all physical logic should have been invisible. In the dim corridors of ESA's mission control, the atmosphere turned electric. The Cassis camera aboard the ExoMars Trace Gas Orbiter had returned a sequence of frames showing a faint, diffuse sphere hovering at the edge of detectability. A glow so subtle it seemed more like a mirage than a celestial body. The engineers, exhausted and cautious, assumed at first it was noise, a trick of sunlight or a burst of cosmic radiation. But as they aligned the images, the pattern held. There it was, steady, real, and astonishingly faint, a blur 10,000 times dimmer than anything the camera had ever been meant to see. That was the first hint that something unprecedented had occurred. For decades, space agencies have sent robotic eyes to every corner of our solar system, each one trained to observe familiar worlds. The volcanic scars of Io, the methane haze of Titan, the whisper-thin storms of Mars, but rarely has a machine turned its gaze outward, into the black, and returned proof of something that did not belong here. The last time an interstellar object was captured in motion was years ago, when astronomers tracked the tumbling shard called Oumuamua, and later the comet Borisov, both visitors from other suns. Yet this time was different. 3I Atlas was not just another traveler. It was luminous, immense, and optically unlike anything ever seen. ESA's announcement hinted at a polarization reading, a measure of how light scatters from dust and ice that plunged into negative territory beyond the known scale for comets, a value of minus 2.77%. To most, that might sound like a statistic. To planetary scientists, it was a cry of disbelief. Negative polarization that strong should not exist. It suggested light was bouncing off matter shaped or composed in ways that defy the rules of physics as we know them. Within hours, speculation bloomed. Was it an instrumental artifact? A calibration flaw? Or had the orbiter truly caught a phenomenon that redefined the behavior of interstellar dust? No one could yet say. But there was another layer to the unfolding drama, the silence from NASA. While ESA's data poured across public channels, NASA's own Mars Reconnaissance Orbiter, which could have provided confirming imagery, had gone dark. The timing could not have been worse. The agency was entangled in a government shutdown that locked its communication systems behind legal protocols. The world's most capable deep space camera was offline just as the most extraordinary object in modern astronomy drifted past Mars. So, as night fell over Europe, the responsibility of documenting this alien wanderer rested entirely with ESA and the amateur astronomers who followed their feed. Scientists across continents refreshed telemetry dashboards and exchanged messages through encrypted links, trying to make sense of what they were seeing. The comet, if it was a comet, refused to behave like one. No tail, no clear jets, no visible fragmentation. Only a soft sphere, glowing faintly against the starlight. The shape alone challenged expectation. How could a body exposed to solar radiation appear so symmetrical, so perfectly diffused? In the following days, that question became the heartbeat of every newsroom, every observatory briefing. 3I Atlas was real, measurable, yet conceptually elusive. The press began calling it the ghost from between the stars. Still, behind the poetry lay the hard edge of data. ESA's team, led by Dr. Lucia Benito, cross-checked the readings again and again. Every wavelength, every filter. The numbers refused to change. Something out there, 10,000 times dimmer than Mars itself, was reflecting light in a way no comet had before. The agency's statement was restrained but clear. The observed negative polarization cannot be explained by current models of cometary dust. That line alone sent shivers through the scientific community. When models fail, so does understanding. And yet, rather than dismiss the anomaly, ESA doubled down. They confirmed the source, confirmed the trajectory, confirmed that the object had passed within 18.6 million miles of Mars just days before. The discovery stood firm. The photographs were genuine. The event was real. What no one yet knew, what no simulation could predict, was why this faint sphere from another star had chosen this moment to appear, and what its strange light meant. Was it merely an exotic relic of cosmic chemistry, or a messenger carrying information about the earliest moments of planetary formation? As the data continued to arrive, one truth became impossible to ignore. Something about 3I Atlas did not fit into the story we thought we knew about comets, dust, or interstellar travel. And somewhere in the silence between agencies, a new mystery began to unfold, one that would blur the line between the familiar and the unimaginable, and remind us how little we truly understand about what drifts beyond the reach of our sun. The images released by the European Space Agency on October 7, 2025, were more than just pictures. They were a rupture in our understanding of how light, matter, and interstellar motion coexist. At first glance, they appeared underwhelming, a faint blur, suspended in the black. But as teams across Europe, South America, and Asia began dissecting the data pixel by pixel, what emerged was a set of properties so improbable that veteran astronomers questioned whether the laws governing comets within our solar system could apply to this visitor at all. 3I Atlas, designated C2025E3, had been tracked for months by ground-based observatories after its inbound trajectory was first spotted near the orbit of Jupiter. Its speed alone raised eyebrows, 134,000 miles per hour relative to the Sun, a velocity too high for any object bound to our system. This confirmed what the early models hinted: it was interstellar, a traveler from beyond. Yet none of the theories prepared scientists for what ESA's ExoMars Trace Gas Orbiter would record. The Cassis camera, built to map Martian rock layers and atmospheric haze, was never meant to resolve faint celestial bodies. Its sensors were calibrated for bright terrain, not for a dim, unfiltered glow beyond Mars's horizon. But under the direction of engineer Nick Thomas, the team performed a daring experiment, extending the exposure time tenfold, manually tuning the software to track a target moving relative to both Mars and the background stars. Against all odds, it worked. A series of deep exposures taken over several nights revealed the ghostly image of the interstellar visitor. When calibrated and stacked by ESA's data analysts, the composite frame showed a diffuse, nearly spherical glow, lacking the asymmetric tail or jets common to comets. The object seemed cocooned in a luminous haze, its surface scattering light in ways that made little sense. In standard comet physics, sunlight reflects off dust grains and ice particles, producing a pattern of positive polarization. 3I Atlas, however, exhibited the opposite. Its negative polarization value, minus 2.77%, suggested a surface composed of material that absorbed and twisted light, possibly grains of an exotic geometry or chemical makeup unseen in the solar neighborhood. To confirm this, ESA conducted cross-references with spectral data from Earth-based telescopes in Chile and Japan. The Very Large Telescope and the Subaru Observatory both detected unusually strong emissions from carbon dioxide, but at wavelengths shifted by tiny fractions that implied something dense and metallic was influencing the light. A parallel study by the Max Planck Institute attempted to simulate the scattering behavior using models of porous silicates and nickel-rich compounds. None matched the results. The conclusion was unsettling. Either the dust around the object possessed properties alien to any known comet, or the light was being modified by electromagnetic phenomena not yet understood. Dr. Lucia Benito, head of imaging operations at ESA's Mars Center, described the moment they confirmed the readings. "We kept recalibrating," she said in a later interview. "Every assumption failed. The numbers remained stubbornly impossible. That's when we knew we were seeing something outside all precedent." Her statement echoed through universities and observatories, prompting a flurry of independent verification. Citizen astronomers worldwide joined the effort, downloading ESA's raw image sets to test the processing chain. Using open-source algorithms, they verified the presence of the faint elliptical glow in precisely the predicted coordinates. None could reproduce it as an artifact. The anomaly was real. By mid-October, over 200 observatories had contributed data. Triangulation confirmed that 3I Atlas had passed within 18.6 million miles of Mars, an interplanetary hair's breadth, before curving sunward. The estimated mass was colossal, more than 33 billion tons, roughly 1,000 times greater than Halley's Comet. The nucleus alone spanned between 3 and 5 miles, but the coma, that mist-like envelope of gas and dust, extended hundreds of miles outward in an almost perfect sphere. Most comets, heated by sunlight, produce tails blown backward by the solar wind. Atlas showed no such feature. Its coma remained compact, cohesive, and eerily stable. Surface brightness data intensified the mystery. Even as it approached the inner solar system, its light output barely changed, suggesting an object impervious to thermal stress. Infrared readings indicated an albedo, the measure of reflectivity, far lower than any known comet, nearly as dark as charcoal. And yet, surrounding this blackened core, the scattered halo emitted faint, negative polarized light, a contradiction in itself. To reflect light negatively, the particles must be both minuscule and shaped irregularly, like shards or filaments, possibly metallic. Some suggested the grains might contain crystalline nickel sulfide or other exotic compounds formed in supernova remnants. Others proposed something more startling. Materials engineered rather than natural, the residue of an artificial alloy weathered by cosmic radiation. These speculations might have remained fringe if not for the supporting spectral evidence. ESA's partnership with the Spherex Infrared Observatory revealed discrete emission lines corresponding to nickel without matching lines of iron. In natural cosmic formation, these elements are born together in the hearts of dying stars. To find nickel in isolation implies a process of separation, either physical or chemical, that does not occur spontaneously on such scales. When researchers presented these findings at an emergency symposium hosted by the European Southern Observatory, the debate turned fevered. Some argued that unique conditions in interstellar molecular clouds could explain selective survival of nickel compounds. Others, including the controversial astrophysicist Avi Loeb, proposed that the data hinted at deliberate refinement, perhaps relic dust from a technological civilization long gone. Meanwhile, ESA's internal teams avoided speculation and focused on the motion itself. Tracking the object's trajectory revealed something even more puzzling. Despite venting gas from multiple jets, its path remained almost perfectly linear, deviating less than 50 feet per day from predictions. An infinitesimal shift for a body moving at over 100,000 miles per hour. Normally, such outgassing acts like miniature thrusters, altering a comet's orbit unpredictably. The near-zero deviation implied extraordinary mass or internal cohesion, possibly a solid, monolithic nucleus rather than the fragile, icy conglomerate comets are known to be. Theoretical models by the University of Heidelberg calculated that the object's tensile strength had to exceed that of any natural ice-rock mixture by a factor of 50. Adding to the intrigue, the trajectory lay within 5 degrees of Earth's orbital plane, the ecliptic, and intersected the sky coordinates near which the enigmatic "wow" signal had been detected in 1977. Statistically, the odds of such alignment by chance were less than 1%. To most astronomers, it was coincidence. Yet coincidence on this scale tends to provoke deeper questions. Was 3I Atlas merely a passing stone, or a fragment of something far older, something that once moved with intention? The technical process behind these observations became a story in itself. Because NASA's Mars Reconnaissance Orbiter and its HiRISE camera were offline, ESA coordinated with independent satellite operators to compensate. Data from Mars Express, the JUICE mission near Jupiter, and Earth-based deep space antennas were synchronized into a joint observation grid. The effort marked the most complex interagency collaboration in the history of cometary science, even without direct American involvement. Engineers described the data flow as a symphony of improvisation, one instrument falling silent, others rising to fill the void. Every available instrument, from the infrared eye of the James Webb Space Telescope to small backyard telescopes on Earth, turned toward the visitor. On October 10th, the James Webb Operations Center in Baltimore interrupted its scheduled exoplanet survey for an emergency override, focusing its near-infrared spectrometer on the faint glow. Within hours, it recorded fine-grained spectra showing molecular CO2 jets extending more than 200,000 miles from the nucleus. But instead of a diffuse outflow, the gas appeared as sharply defined streams, structured, almost geometric. Some of the jets formed circular arcs, suggesting that they originated from specific long-lived vents rather than random sublimation spots. The geometry was so precise that several researchers remarked it looked engineered. As Webb's data reached Europe, cross-validation with ESA's ExoMars measurements confirmed the pattern. At least 6 primary jets emanated at regular intervals around the object's equator, each maintaining its shape over consecutive rotations. The rotation period itself was another anomaly, less than 5 hours, surprisingly fast for a body of that mass. At such spin rates, a normal comet would fragment under centrifugal stress. 3I Atlas remained intact, implying internal bonding far stronger than ice and dust could produce. This resilience extended to its optical signature. Polarimetric measurements showed no change in the negative value even as the object brightened slightly near perihelion. In most comets, polarization varies dramatically with viewing angle and solar distance. Here the curve was flat. The implication: whatever material composed the coma was dynamically stable, possibly magnetically aligned or bound by electrostatic forces. Theoretical physicists at the University of Leiden proposed that the object's surface could carry a residual magnetic field, fossilized from its birth environment in another stellar system. If so, the interstellar magnetic flux might interact with solar wind in ways we have never observed before. Beyond the data and the theory lay a growing sense of urgency. 3I Atlas was on a fast inward arc, due to reach perihelion, its closest point to the Sun, by October 30th, 2025. Once it passed, the glare of solar radiation would render observation nearly impossible, and any structural instability might destroy it completely. The countdown began. Across the world, observatories synchronized schedules for a final coordinated campaign. Even amateur astronomers in backyards joined, capturing long exposure traces that later contributed to composite models. The global collaboration became the most extensive ever organized for a single interstellar body. Still, the unease persisted. Each new dataset seemed to confirm the strangeness rather than resolve it. The nickel-dominated spectra, the absence of iron, the impossibly cohesive coma, the geometric jets. Together they painted a portrait of an object that should not exist according to known astrophysical laws. Some theorists propose that it might be a fragment of a protoplanetary seed, the kind of dense core that sparks planet formation in young systems. Such an embryo, torn from its birthplace, could wander the galaxy for millions of years before being captured briefly by our sun's gravity. If true, 3I Atlas might carry the chemistry of alien worlds yet unborn. But there was another, more speculative hypothesis circulating quietly through scientific circles. A few researchers whispered that the object's structure resembled not a comet at all, but a shell, a hollow fragment, perhaps metallic, sheathed in mineral dust. It was conjecture, unsupported and dangerous to state publicly, yet the idea lingered. The pattern of outgassing jets, the uniform rotation, the persistence of negative polarization, all could, in theory, arise from reflective panels or cavities aligned with precision. A natural explanation remained elusive, but the scientific community, bound by rigor, continued to search for one. As days passed, the blackout of NASA data deepened the mystery. Without access to Mars Reconnaissance Orbiter's imaging archives, independent teams could not compare the perspectives needed to construct a full three-dimensional model. The gap created a void, one filled by speculation, debate, and mounting fascination. ESA maintained a tone of calm professionalism, releasing incremental updates while urging patience. "Extraordinary data require extraordinary care," their statement read. "Our responsibility is to ensure accuracy before interpretation." In the meantime, an unexpected observation came from the Perseverance rover on Mars. Its sky camera, designed to monitor atmospheric dust, caught a faint moving object against the dawn horizon. A slow, steady trace consistent with the projected path of 3I Atlas. The image, though blurry, matched the comet's brightness profile perfectly. It was the first time an interstellar object had ever been photographed from the surface of another planet. For researchers, it was a poetic moment. A robot built by humans on one world capturing the shadow of something born between the stars. By late October, as the object drew closer to the sun, light curves from multiple observatories showed subtle pulsations in brightness, repeating at 5-hour intervals, the same period as its rotation. Whether these were caused by jets, reflective facets, or internal structure was unknown, but the rhythmic dimming gave the comet an eerie quality, as if it were breathing. ESA's control center nicknamed it the heartbeat of Atlas. Each new image, each spectrum, each telemetry burst tightened the web of questions. How could an object so massive maintain perfect composure while spewing gas into the void? Why would its light twist into negative polarization values no mineral mixture could produce? And perhaps most hauntingly, why did its trajectory align so precisely with the plane of the planets, as though it had chosen this path deliberately? No answers came, only data streaming endlessly from spacecraft and telescopes alike, whispering of a reality more complex than the models that sought to contain it. As the world watched, 3I Atlas continued its silent approach, its strange glow growing marginally brighter against the darkness. In every lab, from Darmstadt to Pasadena, the same realization settled in. This interstellar visitor was rewriting the rules. Whether through accident or intention, it had revealed that our solar system is not as isolated, nor as well understood, as we once believed. What awaited at perihelion would decide whether 3I Atlas survived the sun's furnace, or dissolved into vapor, taking its secrets with it, leaving humanity once again to wonder what other wanderers drift unseen between the stars. To understand why 3I Atlas has shaken the scientific world so deeply, one must look beyond the photographs and numbers and see the people and machines that made them possible, and the strange lineage of discoveries that led to this moment. The ExoMars Trace Gas Orbiter, now immortalized as the spacecraft that captured the impossible, began its journey in 2016 with a simpler dream: to study the thin whisper of Mars's atmosphere, to search for traces of methane and unravel clues to the planet's geological past. It was never designed to glimpse interstellar ghosts. Its camera, the Cassis instrument, built under the supervision of engineer Nick Thomas and his team in Bern, Switzerland, was meant to photograph the deep reds of Martian rock, not the cold black of space. Yet from this unassuming platform came a revelation that now stretches across every field of planetary science. Nick Thomas himself has worked on space imaging since the early 1990s. In interviews given after the release, he described the challenge of tuning a camera built for bright landscapes to catch a target more than 10,000 times fainter than any planned exposure. "It was like trying to photograph a candle from across a continent," he said. "You push the instrument to the edge of what it can survive and you hope it doesn't fail." The success of his experiment was not luck but persistence. Long nights of recalibrating focus, timing exposures, compensating for the orbiter's slight tremors as it drifted through Martian orbit. The image that reached Earth on October 7th carried not only data, but the fingerprints of every person who refused to give up when the numbers seemed impossible. In another part of the story stands Dr. Lucia Benito, the mission's science lead. She came to ESA from Spain's Institute of Space Astrophysics, having spent 2 decades studying comet dust and light scattering. Her work on polarization had once been considered a niche topic, a quiet corner of optical physics. Now it sits at the heart of a global mystery. Colleagues describe her as calm, analytical, and quietly relentless, the kind of scientist who measures every word but never loses sight of wonder. In a recorded message from ESA headquarters, she said, "We built Cassis to look for faint reflections of Martian cliffs. It looked farther, and it reflected us instead. Our drive to keep looking, even when we think we know what's out there." That spirit of curiosity has long defined humanity's relationship with the cosmos. From Galileo's trembling telescope in the 17th century to the orbiting observatories of today, every instrument we send skyward is an extension of our collective question: what else exists? But 3i Atlas has forced that question into sharper focus. It challenges not only our technical limits, but our assumptions about how the universe builds itself. Its negative polarization defies optical models. Its nickel-heavy composition defies stellar chemistry. Its unyielding trajectory defies gravitational common sense. And yet, despite these contradictions, it remains a coherent object, moving with purpose through the solar system like a stone carried on an invisible tide. ESA's archives now preserve terabytes of data from its brief encounter, a digital monument to a cosmic event that may not repeat for centuries. Scientists across continents continue to study those files, tracing the fine threads of light and motion. At the University of Cambridge, Dr. Ria Sokolov's team has simulated over 100,000 scattering models to reproduce the polarization curve. None fit. "We are missing a property," she admitted in a public lecture. "Either a physical characteristic of matter we have never seen before, or an interaction we have never measured. That is both terrifying and beautiful. The fascination has spilled far beyond academia. Amateur astronomers who once chased meteor showers now aim their lenses at the patch of sky where Atlas once burned faintly. Social media feeds fill with time-lapse composites and spectral overlays. Artists and filmmakers render its ghostly glow in digital animations, trying to capture the feeling of seeing something truly alien yet undeniably real. For many, it has reignited a cultural awareness that the universe is not static, not a silent backdrop, but a living, moving ocean where strangers drift through the void. As ESA's data continues to circulate, NASA's silence has taken on a life of its own. The temporary shutdown that locked their Mars Reconnaissance Orbiter's data during the event remains a sore point for scientists who understand what might have been seen. Some insiders have hinted that the MRO's instruments did record images before communications ceased. But until those archives are restored, the world may never know what the American cameras saw. What is known is that the absence of one voice gave rise to another. ESA's leadership, usually cautious and reserved, stepped into the spotlight with a level of transparency rare in modern space science. They released raw data, calibration logs, and mission notes, inviting independent verification from anyone capable of analysis. In doing so, they turned a closed investigation into a global experiment, a gesture that may reshape how future discoveries are shared. Now, months after its closest pass to the Sun, 3I Atlas has faded from easy view. By December, its light had dimmed beyond the reach of most telescopes, slipping back into the darkness between the stars. Yet its influence lingers. Papers flood the journals, arguing over the meaning of its composition, its motion, its improbable stability. Some call it a condensed fragment of a shattered exoplanet, its metals refined by pressure and time. Others see it as a frozen embryo of a world that never formed, carrying the chemical blueprint of life from another system. A few dare to whisper the untestable, that its geometry and persistence hint at construction rather than chance. But in every theory, one truth repeats: the universe just became stranger. In the halls of ESA's mission control, a small team still works late into the night reprocessing the final data before the comet vanished behind the Sun. They know that when the object emerges again, if it survives perihelion, it will already be outbound, leaving the solar system forever. Its next encounter with another star could take millions of years. What remains here are only the echoes, the photons that brushed its surface and traveled to our instruments carrying secrets of a chemistry and structure older than Earth itself. To the scientists who witnessed it, this is not a story of mystery alone, but of perspective. 3I Atlas is a reminder that interstellar space is not empty. Between stars lie countless fragments of creation, seeds, relics, travelers, carrying the memory of distant suns. Everyone that enters our system offers a chance to see what other worlds are made of, how matter organizes itself when no one is watching. And everyone forces us to confront the possibility that the patterns we call natural may not be universal. As the data settles and theories multiply, one emotion unites those who watched this discovery unfold: awe. It is the quiet, humbling realization that for all our satellites, sensors, and equations, we are still newcomers in a cosmos vast beyond comprehension. We peer through narrow windows, catching glimpses of infinity one anomaly at a time. In the final analysis, 3I Atlas may prove to be a natural fragment, a survivor from a distant planetary nursery, or it may remain an unsolved puzzle, a reminder that our tools are not yet sharp enough to slice through the mysteries of interstellar matter. But what it has already done is undeniable. It has bridged worlds, Mars, Earth, the empty gulf between, and linked the work of engineers, scientists, and dreamers into a single shared moment of discovery. It has shown that even in the silence of space, there are still stories waiting to be found. Stories written in the language of light and dust, waiting for eyes brave enough to look. When future generations study the annals of astronomy, they will see October 7th, 2025, marked as the day the universe blinked back, the day an unassuming orbiter designed to photograph Martian valleys turned its lens toward the unknown and caught a reflection from the deep. In that reflection, humanity saw not a mystery to fear, but a challenge to understand. And perhaps that is the truest legacy of 3I Atlas. It reminded us that exploration is not about finding answers, but about asking better questions until the stars themselves begin to answer.